thanks everyone for attending to this talk today. I'm Gabriele Belotti, I'm a PhD student from Politecnico di Milano. And let me first say that I'd like to thank Creatis Lab and Simon Reed for making this work possible. And so starting from some background on the application scenario, I will try to be quick about it. So as most of you know, radiotherapy involves the use of ionizing radiations to treat cancer. And one of the backbones of conventional photoradiotherapy is the unfavorable release of radiation to the surface of a targeted body, in this case, healthy tissues of a human being. And this is described in the image. Let me try and get pointer. This is described by the dose depth profile of the for photons here, for X-ray photons. And this graph also shows you the nice advantage of the other technique, which is hadron therapy, which is called this break peak. And of course, I expect you to know about it, but it's this energy-dependent peak of release that gives hadron therapy using carbon ions and protons such nice precision in dose delivery. And so here's my indication of the higher geometrical selectivity of this therapy. This also comes with a greater biological effectiveness, meaning that the dose that is transferred to the patient is more effective. But of course, this nice plus in hadron therapy comes with a great drawback, and this is the higher sensitivity to errors that lead to the necessity of taking this into account during treatment. So usually to deal with uncertainties, you of course need a planning CT on which you draw contours, you draw the beam direction and the dose map. But this is not enough. Of course, you need an in-room verification system. Often this is a cone beam computed tomography image acquired with a scanner that is placed inside the treatment bunker. So I forgot to mention I work with the CNAO Treatment Center, and CNAO stands for Centro Nazionale di Hadroterapia Oncologica. So it's a hadron therapy center located in Italy, in Pavia. And it was created in 2001 and started clinical trials in 2010, ended in 2015. CNAO possesses a synchrotron, which has 4 fixed beam lines, 1 vertical, 3 horizontal, and those are connected to 3 different treatment rooms. And keep in mind that this means that there's no rotating gantry at CNAO. And when the central room, the one with the vertical line here, was commissioned, a decision for the adoption of an in-room verification system was to be taken. So at the time CNAO did a survey, there were several solutions to meet the in-room verification requirement. So we have the classical options of having gantry-mounted CBCT of an oscilloscope-mounted CBCT, which are not an option at CNAO because, as I said, there's no rotating gantry. Then we remain with the robotic C-arm CBCT system option, the in-room CT on rail option, and the couch-mounted CBCT. But of course, the in-room CBCT, the in-room CT on rail was not an option because the bunker was too small and with a large patient positioning couch. So this was not an option. And the couch-mounted CBCT was an expensive solution that at the time was still in the first development stages. And so CNAO decided to ask Politecnico di Milano to develop a custom robotic C-arm to be placed inside the bunker to acquire CBCT. So here we have an image of the system. It's a robotic manipulator from Kawasaki that was fitted with a C-arm, customly made. And on this C-arm, you can, well, maybe later we have a better image, but there's a flat panel detector mounted on it and an X-ray source with a collimator. The problem is that this was mainly used for 2D, 3D registration, so to acquire planar X-ray, orthogonal X-rays, and with the plus of a CBCT to be acquired in anatomical verification cases. The problem is that the field of view is limited. This is one image of a patient pelvis acquired on this system, and you can see that you cannot discriminate very well outside this green circular FOV in the axial plane. And so apart from that, another problem that we must take into consideration is the limited range of motion given by the encumbrance of objects inside the treatment room. So use a nice video of the system in motion. What you cannot really see here is that there is a peninsula connecting this arm of the robotic couch to the central part that has the possibility of getting hit by the X-ray tube. So the decision was taken to just limit the range of motion to 220 degrees. So taking a look at the geometry of this acquisition in the z=0 plane. Supposed to show it. So you can see this is a classical full fan geometry as is often described. And you can see that in this case, I put an I and O to be superimposed. I representing the isocenter of the imaging system that you must take into consideration is the tooltip of the robot. So it doesn't really have to be there all the time. It can change position since it's a robotic manipulator. So of course, the circular trajectory is imposed to the source, and the FOV radius, calculated with a little bit of trigonometry, is of 102 millimeters. As I said, insufficient. As I said before, to reconstruct, no, actually, I didn't say it before, sorry. So to reconstruct analytically a range of motion that is under 360 degrees, so a case of a short scan, you need to account for redundancies, and this is done through a redundancy map. Here we have an image representing it. So this is a redundancy map of a row of the detector in the z=0 plane, and you can see that it has three areas. The central area, basically, it's equal to 1, and it represents the fact that rays measure points only once. You don't really need to do anything about it. But there are two areas here where you need to compose your rays for points that are traversed twice during acquisition. So nothing really interesting here. To augment the FOV of a system, of a CBCT system, usually we have the displaced detector geometry, or ALF-FAN often called, which stands for a geometry that displays the detector while leaving all other things untouched, and by chasing the detector with your emitted beam, you can enlarge the FOV. So what's the problem here? Of course, we need a flat panel detector that is able to be displaced, and also an adjustable collimator. Given that we also need a redundancy weighting map, which was already described in literature by To and Wang. Here we have a map of these. It's very similar to the short scan weighting concept, just handling the offset detector condition. And you also need a full scan. So 360-degree rotation to be able to reconstruct this analytically. And so we don't have a displaced detector, we don't have an adjustment collimation, and we don't have a full scan. So how do we solve this? Going a little bit further, we can look at what's called the displaced center of rotation geometry. And in this case, you can see how the isocenter is not fixed on the center of an image anymore and follows a circular trajectory, a small circular trajectory. The source still follows a circular trajectory. And we introduce a small factor called tau, which is the tilt angle. So there are previous analyses of FTK implementation that account for both fixed and gantry angle dependent tilt. Such tilt can be achieved and kept constant during a full scan rotation by the CNAO robotic system. But at the same time, the source trajectory remains circular, although it is a little bit larger from the conventional case. So what do we need to reconstruct? The displaced detector and adjustable collimation, no more. The redundancy weighting still, but we had that already, and Wang accounts for this. We need a compatible FTK implementation, but we have that in RTK. But we still need a full scan. So this is still not an option for a CNAO system, or at least it's not practical unless we can find it a way to have the 360-degree rotation in a safe way for the patient. So we arrive at our proposal finally. And our proposal is to do what's called a complementary displaced center of rotation acquisition, meaning that we want to combine two displaced center of rotation acquisitions that have equal and opposite tilt. And we do it so that the source traverses the same arc of trajectory. After the acquisition, projections are weighted according to our implementation of the Wang's weight for the displaced detector. And they are also weighted for the Parker shot scan weight, depending on the source position and the incidence angle alpha u. So we are combining both the short scan and the displaced detector weights. The whole procedure that includes 2D FTK weighting, RAM filtering, back projection is conducted separately for the first and second acquisition, and then the two partial reconstruction are summed together. To prove this, we simulated a likely acquisition using the forward projection of a numerical generated phantom. So this is the four-bill thorax phantom, and it was projected into two stack of projections, G1 and G2. The range of motion is representative of that of the CNAO case, so it's around 212 degrees. So we do have overscan as well. It's not just a short scan with the bare minimum. And here we can observe the redundancy map on top, which are the result of the redundancy map for short scan convolved with the displaced detector map for the first and second motion respectively. And at the bottom, you have the two partial reconstruction that I told you before the summation. So after we sum the contribution, that's what we get. And here we have a comparison of what's the FOV you would get on a conventional geometry for the same phantom. We extracted profiles from the central slice, the axial, coronal, and sagittal slices, which are conformal with the ground truth, which is the first row here represented. So qualitatively, we were quite happy. There is a degradation which is consistent with the FTK approximation along the axial direction. Maybe here it's not well represented, but it's consistent. So we decided also to calculate the mean absolute error. And this didn't give much information by itself. So we decided to compare the method with more conventional solutions. And so the results for them are here represented. So we calculated the mean absolute error for the whole volume in the FOV for the 3 methods. And we have a classical Alphan approach over a 360-degree scan and a so-called wide full fan that basically it's a way of saying that we double the size of the detector and the internal fan angle. Also, you will see that the results for our proposal and the wide full fan are really, really close. And this is due to the fact that we try to impose the source position of the wide full fan acquisition simulation and our proposal to be the same, not just to have the same arc span. So in the end, what we achieved was a FOV extension that doesn't need any hardware upgrade. And we evaluate this on a 3D numerically simulated data, and we compared it with other conventional methods. In the future, what we will have to do is to acquire real data, possibly a Cheers atom is what we are gonna acquire. And we need to account for geometrical fluctuations of the system during the motion. And possibly there will be a need for scatter evaluation and eventual correction. So that will be all. Thank you for listening. And I'm here if you have any question. So we did all of this in 3D. So maybe I failed to stress this enough. So yeah, here you can see the the central axial slice, but then you have the coronal and the sagittal slice that show how we had the full reconstruction for the so getting away along the Z direction, of course, if that's what you're asking. Yeah. Yeah, this is just an FTK to show you in a maybe unfair way, but it's a way of showing you where the FOV would stop. And of course you have a lot of truncation, but it's just to show on the same phantom that we used to conduct the simulation, what it would look like if we didn't use an iterative method of something that is capable of handling truncated data. Yeah. Yeah, sure. No, I agree. This is a bit unconventional, I would say, to just show you this result. There's a better way to do it and to reconstruct the FOV inside here without having this truncation effect, these border effects. I totally agree. Artifacts you get from standard Complementary geometry, and you move away from central plane, start thinking going back, you wrong. Can you point here where they're going wrong? I don't see anything. No, I think this is not the best grayscale. I think it's a bit compressed to show you. But yeah, usually here it's just slightly visible. You have a bit of I mean, sorry, the ground truth is not reconstructed through the FTK, of course. This is just drawn because it's numerical phantom, so you don't have any artifacts. But here you do have some artifacts, and I guess here as well you might see some artifacts around the spine of this thorax phantom. So the warm artifacts probably being suppressed by the grayscale. Yeah. But they are still there. So
you know, so everything's based on cell cap. You're essentially doing a short scan in the cell cap job. Okay, you have to stitch together detect spaghetti.
Yeah, exactly.
That works, but wait, but the real question is why you use cell cap for short scan. You cell cap theoretically correct to do it. Well, correct in the sense that it's doing the best it can with data. You have a 360 scan. When you have a short scan instead of 360, then you can also function the rays that are measured in the cell cap zone. So in the central plane, you exactly the same set of rays, but when you look at the plane above the central plane, with a full 360-degree cell cap geometry, every ray is only measured once.
Yeah.
So in the central plane, every ray is twice the things that short scan or offset detector. But anytime you do those, you're removing some rays that would present in the 360-degree cell cap geometry. So you have less information as a result. In 3 dimensions, you have less. In 2 dimensions, you have fewer measurement lines. Okay. So then the question is, why would you apply cell cap? This would be the part of free state. Don't trust cell cap. Why don't you get rid of free structure now? You should get a line to the best you can. Then that would be my suggestion.
Okay. No, so, well, I would first point out, so, but then if I have an object that is inside the FOV and can be acquired with a normal full fan geometry strategy, would it be bad to just use a short scan, just to understand your point of view? Yeah, in 3 dimension would be bad as well. Yeah, but would it be bad to acquire, let's say, a head of a patient with a 220-degree full fan scan? You would rather use iteratives to reconstruct them. I mean, I see your point, and iterative is always a good solution. But in clinical practice, speed is very valued. And I know that's the main reason, and you expected this answer.
That's an excellent answer.
Okay. No, I see. But so in the end, okay. So what you're saying is that the wide full fan case, I mean, now I'm extrapolating what you're saying, but so if I wanted to have a nice comparison with an actual ground truth, I should have used the wide full fan that does a complete 360-degree scan. Okay, that's okay. Yeah, that's interesting. I will probably try and implement this as well. Thanks for the question.
Any other